There is a three types of configuration in case of BJT. The configurations are common base configuration, common emitter configuration, common collector configuration. It is called CB configuration, CE configuration, and CC configuration. So here we consider PNP transistor to understand the configuration contours of common base, where base, which is N, is common, depend on the E, respect to the E and respect to the C. Similarly, in common emitter, where emitter is common, respect to B and respect to C. Depending on that, the emitter base voltage is VEB and collector and base voltage is VCB. This is the or in circuit, input circuit, or this is the output circuit. This is the input, this is the output of this configuration. Whereas in case of common emitter, the input voltage VEB, emitter base voltage, which is input, and output is VEC. Similarly, in case of collector, common collector, whereas collector is common respect to the base and emitter. So here current is IB and IE, emitter current. So voltage, input voltage VCB denoted by VCB and output voltage denoted by VEC. So here VCB, input voltage. So this is the configuration. So using this configuration, we discuss briefly next day. Today we try to understand the current flow in the BJT. So now we see operation in thermal equilibrium in common base. There is a three configuration. So we here consider common base. In case of common base, the base terminal is common respect to the emitter and collector. So in case of operation of thermal transistor, the emitter base junctions for the normal operation junction is always forward bias, and this is the forward bias and this is the reverse bias. So current flow normally. So how it is, you see right now here explain that PNP BJT is considered PNP emitter where the heavily doped, base or the doped less than E, 10 to the power 17 at 10 to the power 19, collector 10 to the power 15. So there is no current flow in case of equilibrium condition, because you see again we can hear two junctions J1, P and N. So if you remember the function of the PN diode, or how to you form the diode depletion layer. So you same way, this is the charge, this is the rho density of the charge, this side and this side. So depletion layer, you see depletion layer, this side is larger than this side because this is the heavily doped than this. So in case of low dope, we know the depletion layer is larger than the high doped region. So you see according to the picture, this is the this width is the low than the or small than the this width. Okay, similarly here you see P and N. So N is the heavily doped than the P. So N here, this one. So this is the very small than this. Okay, same from here we can find out electric field. Okay, same way in case of PN diode, because it is PN diode, again this is PN diode, there is a two junction JN and J2. So here another things is that energy band diagram. So how do we draw the energy band diagram? Because it is P, it is P, it is P, it is N. So here first we draw the Fermi energy level, then we draw the valence band, closer to the EF. This is P, this is N, this is P. This side also closer to above EC, above EC. In case of N, EC is the closer, and below this is the EV, and at the depletion layer it is bent from P side to N side. You see in case of PN junction diode, the bending from the P side to the N side. So here P side to the N side, and you see here this is P, this is N, so P side to the N side is bending. Okay, and this is the flat because due to the this depletion width is a larger than this. Okay, this way we can draw the energy band diagram. Okay, in case of BJT. So hope you understand about the energy band diagram of the BJT. So you can draw the any kind of energy band diagram in terms of energy band diagram in BJT, in case of NPN, in case of PNP, in case of common base configuration, common emitter configuration, you can draw the energy band diagram same way. So there is a different mode in case of BJT. So one of the mode is active mode. There is a saturation mode, you know, cutoff mode. So first we see the operation in active mode in common base configuration. So in active mode, what happened? The emitter base junction is forward bias. You see, this is the P, this is the N. So P connect with the positive, N connect with the negative. This is forward bias. And whereas base collector junction is reverse bias. This is positive, which is connected with the base. This is negative, which is connected with the collector. So depending on that, if it is forward bias, what happened? Then this depletion layer is decrease, it tends to 0, whereas it is reverse bias. So depletion width at the collector side is increase, both side increase, but more increase in the collector side. This is the reverse bias. Okay, so depending on that doping profile, like this picture, an electric field like this picture. So in case of energy band diagram, what happened? This portion is decrease than the previous diagram, whereas this is the increase due to the reverse bias. So if you think about the current flow with this diagram, you can explain, and if you can think with this diagram, you can also explain. So what is the explanation to current flow? So depending on the biasing, so this is very small, negligible. So this is the higher concentration of holes, P, and here electron is the minority carrier, hole is the majority carrier. So holes move from this emitter to base, whereas N is, in case of base, electron is the majority carrier and hole is the minority carrier. So holes move from the E2 emitter to base. So the number of holes is very large. Some holes are recombined with the majority carrier of electron in this region. Maximum carriers holes are accumulated in the base. But here, due to the reverse bias, the electric field from the N to P. So due to the electric field at this junction, the holes, these minority carriers move from base to N immediately. So here P is the collector is the P. So hole is the majority carrier, electron is the minority carrier. So here this holes from the base to collector is moved due to the electric field. So current flow from the emitter to collector through the base, where base is only the control this current depending on the biasing. If the current IB, the minority carrier is increased, the recombination, majority carrier is increased, the recombination rate is very small. Due to that, whatever the current is flow, that is only the IB. Otherwise, maximum current flow from the emitter to, or carrier is flow from the emitter to collector. So that's why we see in case of practical session that IB is very small, that is in terms of microampere, and whereas collector current or emitter current is in terms of milliampere. So similarly, if you see here, in this case, here holes is the majority carrier. Okay, this is P, this is N. Okay, so in case of hole, you see this is the downhill for the hole. This is a downhill for the hole. So hole easily move from this side to this side. So same things I think describe here. Depletion layer width of the EB emitter base junction is narrower and CB junction is wider compared with equilibrium case. Previously we discussed about the operation in case of equilibrium. So here is the non-equilibrium, which is called active mode, where we apply the forward bias in emitter base junction and reverse bias in base or collector base junction. So emitter base junction is forward, holes injected from the P plus emitter into B, result excess holes in B, electrons injected from the N or base into E. So if holes is moved from this side, that means electrons move from this side to this side. Common base junction CB is a reverse bias. If B width is narrower, holes injected from the E can diffuse through B to reach to the BC depletion edge and float up into the C. So when it is reverse bias, that means this depletion layer increase. So neutral region is decreased. So there is no scope of storage. It is move from base to the collector, or otherwise you can say, depending on the electric field from the N side to the P side, this minority carrier move from base to collector. So here E emitter, C collector, current C, here hole I is equal to emitter holes current. Here right, emitter emits or injects carrier, so collectors collects carrier from nearby junction. So collector hole current, which is near equal to emitter hole current. So emit and collect concept here. Okay, the transistor action, carriers injected from E junction, large I flow in C junction. Okay, so due to some recombination at the base region, there is a IB current is generated. For the IB current, we can say IC near is equal to IE, because of the IB current is very small in terms of microampere. We discuss elaborately the current equation of the BJT next class. So whatever we try to understand, we see here PN transistor. You see red is the hole and this is the electron. So holes move from the emitter side to the collector side, and electrons move from collector side to the this side, where this is the, in case of forward bias, there has happened diffusion, because the depletion region very small in terms of in tends to 0 angstrom. So this is happened due to the diffusion, and at this junction in reverse bias, this is due to the drift due to the electric field. Okay, so here the current flow, electron current generated by the this line, electron flow this line. So electron current if this way, so electron current should be opposite, whereas the current, whole current and whole flow is same direction. So in this case, whole flow from this type side to this side, that's mean emitter side to collector side, where in case of emitter side, which is denoted by IEP, current in emitter due to the hole, and whereas in the base there is a emitter current IEP, and there is a collector current ICP, because there is a minority carrier, electron is moved from this side to this side, so current flow from this side to this side, which is ICN due to the electron, and due to the hole, which is ICP. Similarly here, the current due to the electron, because the minority carrier of electron base to the is moved from base to the emitter, that is the IEN. This is the current component, which is where IE, total IE current is nothing but a IEP plus IEN in this case. Similarly here, total IC current nothing but a ICP plus ICN. Similarly, okay, here the description is here. So you see above previous diagram, you just remember the previous diagram. In typical operation, the emitter base junction is forward bias and the base collector junction is reverse bias. When bias is applied to the emitter base junction, the equilibrium is disturbed between the thermally generated carriers and the repelling electric field of the emitter depletion region. This allowed thermally excited holes to inject from the emitter to the base region. These holes diffuse through the base from the region of high concentration near the emitter towards the region of low concentration near the collector. Next point, the hole in the base are called minority carrier. The holes in the base are called minority carriers because the base is doped n type, which makes electrons the minority carriers in the base. So to minimize the percentage of carriers that recombine before reaching the collector base junction, the transistor base region must be thin enough that carriers can diffuse across it in much less time than the semiconductor's minority carrier lifetime. Repeat, the transistor base region must be thin enough that carriers can diffuse across it in much less time than the semiconductor minority carrier lifetime, so that we see the area of the base is very thin, which is maintaining this portion. You see, you just see this portion. Due to this reason, behind this width of the base is very thin, behind that this region. So the transistor base region must be thin enough that carriers can diffuse across it in much less time than the semiconductor minority carrier lifetime. So if it is larger than that, then what happens? Then the holes move from emitter to base and this recombine here. So few of them move from emitter to collector. Same things in case of NPN, where um, electron, okay, charge flow in BJT is due to diffusion of charge carriers across a junction between two regions of different charge concentration. By design, most of the BJT collector current is due to the flow of charges injected from a high concentration emitter into the base, where they are minority carriers and diffuse towards the collector. So in case of NPN transistor, you see this junction, emitter base junction is forward bias. So this is N, so it is connected with the negative. This is P, is connected with the positive, and emitter collector base junction is reverse bias. So collector is N, so we connect here positive, and this P is negative. So this is the forward bias, and this is the reverse bias. So electron, majority carrier electron move from the N side to the P side. So where in case of P, there is a whole electron as minority carrier. So same concept, few of them is recombined, and all the electron concentration, uh, or electron carrier is moved from P to this N, means collector. So if electron is moved from emitter to collector, then current flow is opposite side. So that current flow this side, current flow this side. So you just see the difference for the NPN and PNP. Okay. And now, sorry. So this is the same. This is the circuit diagram. Same things uh, here. Here we try to give you some knowledge about the game. So figure is same in previous discussion. Here assume no generation recombination is in the depletion region. Okay, so holes injected from E, it means emitter, that means IEP, emitter current due to the hole, largest current component. Most of injected holes will reach collector junction, gives rise collector current due to the hole. There are three base current component, IBB, IEN and ICN. There is the base component IBB due to this terminal, IEN which is due to this current carrier in the base region, N majority carrier, and ICN, there is a minority carrier of the C region, collector region. Due to that, there is a current flow. IBB, here electrons that must be supplied by the base to replace electrons recombined with the injected holes. So IBB nothing but a IEP minus ICP. IEP minus ICP. And IEN, current arising from electrons injected from base to emitter. Base to emitter, however, not desirable, minimize using heavier emitter doping or heterojunction. This is the IEN. ICN, thermally generated electrons that are near the BC, junction edge and drift from collector to the base. Direction of electron current is opposite to the electron flow.